Welcome everybody on Zoom. There's my name there, Alberto. Don't worry about the last name. As Mike pointed out, I've been here at Lamont now for 17 years. And one of my research interests in the last few years has been the measurement of geologic time in different ways. So we'll go over that, but I want to talk about that within the context of these very broad idea of deep time, of the fact that the age of the Earth and geological history is working on a time scale that's incredibly larger than the human time scales that we deal with all the time. So I'm going to start with the Rose Center for Earth and Space at the American Museum of Natural History. I just need to hide something from my screen. Whatever, I'll do that. So I don't know if you ever seen this place. You probably did, right? And this is a really interesting walk that you can go around, where you can go around the planetarium, which is in the big sphere in the middle. And as you proceed through this walk, there's a series of panels that you see along the rail here. And each of those panels says, if the big sphere is in the middle is this thing, then this little sphere here is this other thing, and so on. And so, for example, if the big sphere is the sun, then these balls that you see here, there's Jupiter and so on, and the Earth is probably that one down there. So, and then it keeps going, right? So it goes to, okay, if that sphere is the Earth, then something else is something else, and so on and so forth. But it really gives you the message of how big the universe is. You know, the universe is huge. This is a major discovery of astronomy. It's so much bigger than the Earth. And this is not something that is even generally appreciated to its full depth, okay? But if you go on, sorry, wrong way, okay. But not only the universe is huge, but time is also deep. It's not just space, but time. We inhabit a real instant in the time if we look at the history of the universe, or even just the history of the Earth. So you see this spiral, that's one way to show this. The present is here, and as you go back in the spiral, you go back in time, and at the end of the spiral is the age of the Earth, about 4.6 billion years ago. They have a version of that at the museum, right? There's a spiral. You actually start from the beginning of time, from the Big Bang 13 billion years ago, and you start going, and it's about 300 feet long, right? And what you see here is a scale in millions of years. So every time you take a step, you're walking about 300 million years. And you can just walk down, and this is all of human history on that scale. So if the age of the universe is a path 300 feet long, all of human history. So here we're starting maybe with the beginning of agriculture about 10,000 years ago. It's basically a hair. Okay? So we're inhabiting that little speck in time. And the gist of what I'm going to talk about is how do we know? You know, yes, you know, you just have that. You go to the museum, you see all of these wonderful things. They tell you how old is this, how old is that, and how do we know? So I'm going to start from the very beginning of the ideas on the age of the Earth. So this is Niccolò Steno, who in the 1600s, among other things, he was a real polymath, studied these sequences of rock layers, and he basically put forward this simple idea, the principle of superposition. In a sequence of sediments, the ones at the bottom are the oldest, and as you go up, they get younger and younger. So the sediments are in some way recording the passage of time. So that seems really obvious, right? So it's kind of a, you know, there's nothing to it. Much less obvious is what James Hutton, only a little bit later in the 1700s, made from starting from that very simple principle that sediments are deposited flat, right? And they're deposited underwater, right? And so what did he make of that? He saw the outcrop. It's called Siccar Point. It's on the coast of Scotland near Edinburgh. And he saw what we today call an angular unconformity. So these layers of sandstone that are almost vertical, and above them there's another set of layers which are almost horizontal. And in the middle there's a surface here that separates these two kinds of rocks. And what he realized was that there must have been a sequence of events that gave rise to this outcrop. And you see the sequence up there, right? So we start from at point 1 here, you're depositing the gray rocks. Sometime here, there must have been some great event, what we would call today a tectonic event, a deformation event. For example, all of these rocks were folded. And if you take one piece of these big folding where the rocks are vertical, they must have been eroded, right? So everything must have been cut from the top. So they must have gone above sea level, right? Being eroded. Then sometime after that, the red rocks must have been deposited. So you're back again underwater. Then everything must have been uplifted again, eroded again, and we come to today. So that's sort of a cartoon with the geologist walking over the outcrop here. That's what we see today. And Hutton just asked himself, okay, how long could it have taken to go from here to there? Knowing that rocks are really solid things and that erosion works very slowly and so on and so forth. And so his conclusion was that he couldn't even put a time on that. It was so vast that he had no idea how long it could have taken. The only thing he knew is that it had taken a very long time. And so these are his famous words that we find no vestige of a beginning, no prospect of an end. You know, for all intents and purposes, he could basically say the Earth's, the duration of time was almost infinite, as far as he could tell. And I have that other quote from this wonderful book by Marcia Bjorner, Timefulness, that for geologists, every outcrop is a portal to an earlier world. So you look at an outcrop and you start thinking, okay, how do I get this thing to form, right? Time is going that way from the bottom to the top. How does that work, right? The next discovery that came was that of fossils, or rather of the interpretation of these fossils. Remains or traces of living organisms can have footprints, for example, can be fossils preserved in rocks in the past. And then right after the time of Hutton, William Smith discovered that if you looked at packages of rocks that could correlate, right, they had the same age, they had the same kinds of fossils. And so fossils could be used to basically trace the relative position, right, and therefore the relative age of rocks. And so that's where we were at that point. But clearly, all of these ideas give us relative ages. They tell us what is older and what is younger. There's a couple more simple principles that do that, but we don't have any idea of the actual time lapse, you know, how many years to go from this thing to that thing, right? We would love absolute ages to be able to say that rock is 23 million years old or whatever. And so there was a lot of interest in this, and it has a very long history, starting from the famous or infamous biblical chronology, right, of this Bishop Asher, who just went and calculated all the generations in the Bible and came up with the age of, the date of creation, about 4000 BC or something like that. And then there were others. I mean, the last one is particularly interesting, the cooling of the earth. Lord Kelvin thought that we could date the earth by assuming that it was essentially a molten ball at the beginning of time. And from the gradient in temperature at the surface to back calculate how long it took for it to cool down. And unfortunately, he didn't take into account convection in the mantle and the production of radiogenic heat. So his age was way too young. But so these were the ideas, but the actual final way of determining age comes from radioactive decay. So this was really the big discovery, and that's how we really can tell ages at this point. And so in this example here, you start from a parent isotope, in this case, uranium-238. What you see there is the nucleus with the protons and the neutrons. And when there is a decay event, which can happen at any time during the lifetime, if you will, of one of those isotopes, you create an alpha particle and a smaller nucleus. This is a fission event. That's the thorium-234. And so we call this the parent isotope, and this is the daughter isotope. And if you think of a simple case where, for example, you have a volcanic rock, it solidifies, it forms solid minerals. And let's say you start with only parent isotopes in the mineral. As time goes by, some of those parent isotopes start to decay into daughter, right? And if you look at the ratio of parent to daughter, right, or daughter to parent, that will change through time, right? So at the beginning, you have 100% parents, and then after some time, for example, this is called the half-life, you have 50% of those isotopes will be the parent, and there will be 50% that are the daughter. So the ratio being 1 at this point, that's a half-life, okay? And by basically measuring daughters and parents, we can get back the age at which that volcanic rock solidified. This is the simplest case. There's a very rich literature that I'm not going to get into on how to do this. If, for example, there's already some daughter elements at the beginning, and so on. But this is really the foundation of the first geologic timescale, the first quantitative geologic timescale. This was Arthur Holmes in 1960. And what he did was really interesting. He looked through the literature. So this is this stratigraphy of it goes back to the Cambrian, which is the time period where the first fossils that we can recognize really appeared. The first animals, essentially with hard shells and skeletons, were started at that time. And what he did, he looked in the literature, and on these vertical axes, you have the thickness of different units of different ages. This was the maximum thicknesses that he could find. So the maximum thickness, for example, of this Pliocene period is 21 minus 6, so that's 15,000 feet. In some place, there is that thick Pliocene. In some other place, there is a thick Jurassic sequence. In another place, I think. So if you were to stack them all up, right, you would come to 450,000 feet of rock. There's no one place that has 150,000 feet of sediment, okay? But, these are all the thickest ones, right? And then he collected a number of radioisotopic dates that came, for example, from volcanic tuffs. So these are layers of lithified volcanic ash. And as you lay down sediments, there could be a rain of these volcanic ash, and you make a thin layer of that, it gets solidified, and then new sediment comes on top. So that's like a little time marker, right? And so he did a very simple thing. He said, for example, take that point, that's the age here, 375 million years ago. And it's smack in the middle of this Devonian period, okay? So there's a middle of the Devonian, an age. And then he simply interpolated between here with that smooth curve. And now you can take the top of the Devonian, the base of the Carboniferous, and you can give it a date of 350 million years ago. So this was done in 1960 with very few radiometric dates. You can kind of see that there are the dots in this picture. There aren't too many. There's maybe 10 or 15 or so. But it's surprisingly close to the most recent geological timescale. So I'm going to show you an example of how it's done now as opposed to 1960. And so what you see here is an outcrop exposed. These are two stages in the Triassic, Anisian and Ladinian. This is a case where this was all overturned by mountain building. So it's the bed of a stream, you know. And so the older one is here, the Anisian, the younger one is the Ladinian. And the boundary between these two is when the ammonites that are found, these are these spiral-like shells, fossil shells. So there are two kinds of ammonites in these two periods. So the surface between them is this one, the dashed blue line. So this is Anisian, this is Ladinian. And there are two volcanic tuffs. One is here, one is there. This is 238.8 million years old from radioisotopic dating. This is 241.2. And then you can simply interpolate these two ages and say, well, what's the age of that point? The boundary, right? And the age of the boundary comes down to, the age of the boundary comes down to 241 million years ago. So now we have a way to date all of these periods that were defined on the basis of fossil content. The fossils themselves don't give us the numerical ages, but the radiometric dating does. So, and now we have this very elaborate time scale, okay? We have progressed to this point, and it shows you here 241 million years ago, that's the Anisian and the Ladinian, okay? And so again, if you go back to Arthur Holmes, what did he think, for example, was the Cambrian Ordovician? You know, let's go back in time. But he said, well, that boundary is 500 million years. What do we have now between Cambrian and Ordovician? There it is, and it's 475 about. Okay, so he was pretty close, even with that. Now, this time scale gets refined all the time because there's new measurements, there are new sections discovered, and so on. So there's a continuous refinement of this time scale. Every few years, a new one comes out with slight changes and so on. And so we can then date processes that we reconstruct from the sequence of sediments more and more accurately. And the age of the Earth ends up at the bottom here, about 4.5 billion years. That actually comes from dating meteorites. Because the Earth is a very active planet at the surface, all the rocks get mixed up again. There's basically no rock that on the surface of the Earth that's as old as the Earth itself. Everything's being recycled. Okay. Meteorites tell us instead the age of the formation of the bodies, the first bodies in the solar system. And so they're really a really good way to get to the age of the solar system and hence the age of the Earth. And so this is the dating of a meteorite based on rubidium and strontium. These are other elements with their own radioactive isotopes. And you see the ages of these different minerals inside the meteorite are on this line, in this plot that plots ratios of isotopes. I'm not going to go through how that determines ages, but basically the slope is proportional to age, and the age is 4.5 billion years. So that's the age of the planet Earth. Okay, so that's kind of the, you know, the really big picture. And what I'm going to cover now are two things that are relatively even more recent, at least in principle, of this. And one is the fact that the Earth's magnetic field has reversed, and that plate tectonics has provided us with a time scale for those reversals of the magnetic field, because they're recorded in the rocks at the bottom of the ocean. So I'll go through that, and then I'll go through a new technique, which is called astrochronology, which sees cycles. Oh, what happened? Your screen showed up. Thank you. I can't say I'm looking at this. You took over the screen.
Why?
Oh, you want, you know what? You want to unplug that HDMI. That one, yeah. Okay, hold on. Oh no, it's the Zoom went away. Okay, can I have the HDMI? All right. One moment, technical difficulties.
By the time we edit this, it won't exist.
So the people on Zoom can see the slides, right?
Yeah, yes, we can.
Okay, sorry, there was a bit of a glitch here. Okay, I'm gonna start again. So that's okay, because this lets me introduce this new idea. So how did we come to this realization that the Earth's magnetic field had flipped back and forth during the Earth's history? So it all came at the beginning from the realization that lava flows on the flanks of volcanoes were magnetized. It contain a very small amount of magnetite, one of the very few minerals that are magnetic. And so when the lava cools down and solidifies, the little crystals of magnetite, they're like tiny magnetic needles, right? So when the lava is still liquid or fluid, they can orient themselves, and they orient themselves in the direction of the magnetic field at the time in which the lava chills down. Right? And you can take a sample of this rock, which is very weakly magnetic because of all these tiny crystals, and measure its magnetization fraction. What people started finding was that there were lavas that were, the most recent lavas were magnetized in the same direction as the present magnetic. If you think of little compass needles, the North Pole, the north of the needle was pointed to the North Pole, right? But that some older ones were instead, they were magnetized the other way, as if the North Pole was at the South Pole, okay? So the direction was different. At the beginning, it wasn't clear if this was some strange phenomenon that was just happening because of, for example, of the chemistry and the mineral content of the rocks, or maybe some kind of weathering or something like that. But then people started using dating, radiometric dating, so they could also date quite accurately lava. Then they realized that lava flows from different continents, completely different places. They showed these normal so-called magnetization, which is the same at the present field, and the reverse magnetization at the same time. And so clearly, it had to be the field that had flipped. Couldn't be a local phenomenon, had to be a global phenomenon, because again, it all happened at the same time. Around the same time, it's the big time of exploration of the oceans, with ocean-going ships. And at the beginning, they started towing magnetometers behind the ship. It's towed behind the ship, as you can see here, because the ship is a bit quite metal, right? So the magnetic field is, if you tow it away from the ship, the magnetometer can measure.
I've lost the sound.
In the intensity of the magnetic field, and they were symmetrical. And of course, that was a big question: what's going on here? So this is from 1961, a survey across west of North America. There's Vancouver Island there, so Canada is up here, Washington State, Oregon, and so on, California. And what they did here was very simple. They had a lot of profiles, and they simply colored black where the anomaly was positive, so the field was a bit stronger than the ambient value, and white is negative, meaning the field is weaker. And the axis of the mid-ocean ridge is at the location of these green spots. So you can kind of see the symmetry here, right? You begin to see the symmetry. And at the end, it was realized that yes, this is plate tectonics, right? So in this tune, you're going from the past to the present. You see those arrows that come to the present, and the video is going to repeat itself, so we can start again. And what happens is lavas are formed here at the axis of mid-ocean ridge, and they record the magnetic field at that time. If it was reversed, the needles will point that way, tiny needles, but if it was normal, it would point the same way as today. And so you have these blocks of volcanic rock that are magnetized in different directions. If they go in the same direction as the present field, they will reinforce the present. And so if you go over them with a ship and measure the intensity, it will be a little stronger. But if you go the other way, go against the present field, and so the anomaly will be negative, will be magnetic. And so this is how you could see all of that. And so now the mystery is solved, right? In a sense, those anomalies correspond to these blocks at the bottom of the ocean that are magnetized in different directions. Now, I also said, okay, well, this was the whole discovery here of the fact that the magnetic field that flipped depended on dating. So now you could date these things, right? There was some dating for at least the first ones. These are the most recent reversal that are around. And now you can connect this sequence to the sequence of magnetic anomalies. You can put some dates here. You can begin to date the ocean floor. And this is this is a paper that came out in 1966. The first author is Walter Pittman here, who was at Lamont. He recently passed away, but I was lucky enough to know him, and he was a wonderful character. This is a painting of when he received the Vetlesen Prize. I don't remember in what year he did, but it's a top prize in earth sciences for his discovery. And this is the discovery. They drove these ships, the Altani, through the southernmost Pacific. And by sheer luck, it crossed the ocean ridge in the southernmost Pacific, exactly the right angle. And so the legend is that this was the profile of magnetic anomalies they measured, the ridges in the middle. Legend has it that it was plotted on a semi-transparent sheet of mylar, right? So some of you may remember when you used to draw on mylar. And to make copies, right? And that at one point, the transparent sheet was put on the table upside down next to a copy that instead was like up. And then it was realized that if you reversed it and compared it to the data, you had the same pattern. See this triplet here, see this triplet there, you see that. And so there was this astounding symmetry. What you see down here, the third curve is a model. So if you had these distribution of magnetic blocks, we can calculate what kind of magnetic anomalies you should observe at sea level. Blocks are down, the ridge axis is at about 2,500 meters below the surface. And then it gets deeper as you move away from the ridge. So you can simply calculate what kind of anomalies you would observe at the sea surface. And that's the curve with the anomalies. And you can see it, again, tremendous coincidence. Right? So this pattern has been adjusted, right, to maximize the fit. But so now from the anomalies, you can reconstruct these block models, so-called, and that tells you how when and how the magnet switch. So this is all a function of distance, but if you can date some of these, then of course you have a time scale. And so that's how these time scales started to be developed, starting in the late 1960s. Today, we have a lot more data. So this is from a database that NOAA maintains of all the available shipboard tracks that have magnetic anomaly data. So the tracks are shown in this violet color. The intensity of the color has to do with the date at which they were acquired. So the more recent ones have a darker shade. See these tremendous surveys. These are surveys that were made by the Japanese, for example, recently. You can see that there's a tremendous coverage. Altani 19 was that little thing there. That's the profile that we just saw. And so this is, I'll have a few slides about the research that I do. I finally coming to the present. And so this is a refinement of these time scale that is based on data from 13 regions in the world ocean, where the spreading rate, the rate at which, if you will, the tape recorder is running, you want it to run fast, right? You want to record, if there's a short period in which there's a reversal, if the tape is running slow, it's going to be hard to get a good. Yeah, but if the tape is running fast, I have a much better basis for making measurement. And so this uses all of these profiles that you see, the tiny lines here. And the way we do it today is not by hand, but we basically have a computer algorithm that perturbs this block model down here. So these are positive and negative magnetization, calculates the magnetic anomalies, which are the blue curve, and compares them to the actual measurements, which is the red curve. You can see here how we can adjust the position of these blocks and really match the data, these stats. This is a kind of a Monte Carlo algorithm. And so we can also measure the uncertainty we have on all of those dates. And this is the time scale at the end. It's for the period between about 33 and 84 million years ago. And we have the ages of all of these, and we also have the uncertainty. So that's sort of where this kind of technique in science. So now we can basically date ocean floors. So this shows you, red is the present, the time scale here goes back, and uses kind of a standard, if you will, where green is the Cretaceous, for example, blue is the Jurassic, and so on. So it goes from, of course, the youngest ocean floors are at the axis of mid-ocean ridges. So the oldest Atlantic ocean floor is here. It's about 165 million years ago. And here's the oldest Pacific. The oldest oceanic crust is in this corner of the Pacific. About, yeah, it goes up to maybe 170 plus million years. And also, we can determine the rate at which plates are coming apart. So this is done, and see here you see a map. You see the little numbers are centimeters per year, and the fastest spreading oceans are in the equatorial Pacific, with 17 centimeters per year, you know, something like that. And the slower ones are here in the South Indian Ocean, and it's about 10 times as slow, right? 1.3. Also the Arctic Ocean up here, rather not the Arctic yet. It's the very North Atlantic, south of Iceland, 1.8. And this is how that is done. It's very simple. This is a hypothetical magnetic anomaly profile. You see what's called the central anomaly. The mid-ocean ridge is right here. And we know from radiometric dating that this boundary here, so the last time the magnetic field flipped was 781,000 in 0.78 million years ago. So you can measure how broad is this magnetic anomaly in distance. Suppose that's 14 kilometers. Well, then 14 kilometers divided by the age of that boundary gives you 18 kilometers per million years, or 18 millimeters per year, 1.8 centimeters per year. So the image that we usually give for these kinds of rates is they're as fast as your nails are growing. That's how fast it is. And of course, there's a spectrum. Right? Now, the age of these flips is determined from radioisotopic dating. That kind of was the first way to do it, but there's also this new technique called astrochronology. So that's what I'm gonna talk to you about a little bit. So it turns out that, so if the Earth was going around the sun and there was nobody else around, that would be a perfectly stable orbit, right? Newton's laws tell us that. There would be no perturbation. But there's all our friendly planets around us. What they do is they induce perturbations in each other's orbits. It's like a big dance. And so the eccentricity of the Earth's orbit changes with time. And it changes with a period of about 100,000. There are several periods here, not just a single one. But the more important ones are every 400,000 years and every 100,000 years. What that means is that the Earth's eccentricity, well, the orbits are ellipses, pretty close to circles, all of them, but they're slightly squished. And the degree of squishiness changes with time, from almost circular to less circular, right? And a full cycle takes, and there are cycles that take about 400,000 years and others that take about 100,000. The obliquity also changes. The obliquity is the angle between the Earth's spin axis, right? The plane of the orbit. But it also does that dance. And that dance, a cycle of that dance takes about 40,000. And finally, the Earth's axis also precession. So if you remember how a spinning top goes, right? You can run a spinning top, and what you would see is that the spinning top does not typically stand perfectly. The axis does stand perfectly, but it kind of describes a circle. And the speed at which it describes that circle is much slower than the speed of rotation. The top is spinning really fast, right? But it may precess like that, right? Much slower rate. The Earth does the same thing. It precesses like that. Right now, a full circle like that takes about 25,000 years. And so, for example, right now in the Northern Hemisphere, we have the North Star, right? Wonderful thing. If you can recognize where the North Star is, you can always tell north. Well, if we were to wait a few millennia, it's not going to work like that. The axis is going to point to another star. We will eventually make a full circle and come back to the North Star in 25,000 years. This is not some, it's actually been observed by the ancients, not in the position of the stars, but in what's called the precession of the equinox. The fact that the position of the sun at the equinox changes with time. That's even measurable by simple astronomical observations that the ancients. So, okay, so you have these cycles. So what does that have to do with geology anyway, right? Well, changes in eccentricity, obliquity, and climatic precession, this is a twist, it's not just precession, but it's precession modulated by eccentricity. There are lots of these twists that need to be followed. They cause changes in the amount of solar radiation received at any point at the Earth. For example, suppose obliquity becomes greater. Obliquity is the reason we have seasons, right? That's the famous, slightly misleading plot, right, of the Earth's orbit, which is almost circular. We just move from the sun, right? But the point is that we have solstice, you have winter and summer solstices, we have the equinoxes, right? And the reason we have season is that the Earth's axis is inclined. So during the northern hemisphere summer, the sun radiation comes down at a steeper angle, right? And so we get more energy per unit area on the Earth's surface, and in the winter the opposite happens. But if the Earth's axis was more tilted, then you get more sun in the summer and less sun in the winter. And so the seasonal cycle would be more intense. The winters would be colder, the summers would be warmer. Now, the climate changes that result from these changes can change the kinds of sediments that are deposited. So for example, if seasonal cycle was more intense, there could be more precipitation, more erosion, and you get more more sediments, so-called terrigenous sediments that come from the erosion of pre-existing rocks. And all of that could be recorded in sediment sequences. So sediment sequences can record past astronomical cycles. And we have now a large number of examples where we can see these cycles in sediment. But here's one, the beach on the northern coast of Spain. What you can see here is these sequence of incredibly cyclic sediments. And what has been recognized that the alternations are between limestone, which is typically hard, and marl. Marl has more terrigenous components, where limestone is mostly made of tiny shells of calcareous organisms that accumulate in the future and eventually become solid limestone. So that's a hard rock. Marl is more of a soft rock because it has a lot of clay. And so the rocks that pop up, the layers that pop up are limestone, the lighter layers are limestones, and the darker layers that instead of those are. And so here it was recognized that these marl limestone alternations correspond to precession cycles, climatic precession cycles, which are about 20,000 years. They're organized in bundles of 5 or so of these climatic precession cycles, and those are the eccentricity cycles every 100,000 years. And those themselves are organized in even bigger bundles of about 400,000 long eccentricity. And so here we have this recording of astronomical cycles in sediment. Here's a kind of a detail. I found this picture, but I couldn't find where it comes from. It looks very similar, the setting, to the one that I showed you. And here you can see, again, these are the precession cycles, limestone marl. There's about 5 of them in each 100 kiloyear bundle, and then 4 bundles make 405 kiloyears. So what can we do with this? Well, we can date rocks that way. We can certainly date the duration of certain intervals. So in this example, the measurement of magnetic susceptibility done on a deep sea sediment core taken by ocean floor drilling. Magnetic susceptibility measures essentially how much magnetic mineral is in the rock, typically magnetite again. It's not measuring, the orientation of the grains or anything. It's just saying, okay, how magnetic is this particular sediment. And here you can see these really well-defined cycles, right, as a function of core depth. So the triangles mark the top of these cycles. And here you can see a sine wave of 41,000 years. So in this case, it was recognized that these actually corresponded to cycles in obliquity in the tilt. And so basically you got 15 cycles. So these 376 to 394 or 393 or so meters correspond to 15 cycles, 615,000 years. We just dated that interval. Okay. There are also ways to get, so this is dating the duration, right? But there are also ways to get an absolute date if you tie these durations. The features, for example, in the more complex features in the history of these astronomical cycles. This is the simplest way to get data in this way. And so now we are able also to do dating based on these astronomical cycles. So this is a famous Mark Twain quote, right, about science. So at this point, I think, when I talk about this, I always say the mind boggles a bit. We can do things that, yes, there's a lot coming out of these observations, great wholesale returns of conjecture out of these trifling investment of fact. So how do we know? Is there a way to check this? There's some way that we can see whether we did this right? And turns out there is. Okay, so I'm going to spend the rest of this, and then we'll be done on this very simple little testing. I'm going to go back to history again, to Alfred Wegener, as I'm sure all of you know. He was the first major proponent of continental drift. The book is 1929. And when people talk about Wegener's ideas, they talk about the evidence that he presented in the book that had to do with the fact that South America and Africa match, with the geology on the two sides of the Atlantic, with the paleontological remains being similar up to a certain time and then becoming different, and so on and so forth, right? And in fact, if you actually read his book, which very few people read, it's all secondhand, right? But I actually got the book. First chapter where he talks about evidence on geodesy. Geodesy is the science of measuring the earth, right? And he was a meteorologist, and he spent a lot of time in Greenland. That's actually where he died during an expedition. And he must have done some observations of the longitude of Greenland, and they were repeated observations. And he found that there was an increase in the longitude difference between Greenland and the Greenwich meridian, such that the distance of Greenland from Europe was changing at a rate of 36 meters per year. This is wrong, okay? It's about 2,000 times too fast, okay? So it's really wrong. So we don't know what went wrong with this measurement. The point is that in 1929, geodesy did not have the accuracy to be able to see change, right, of that in reality would have been more like, this much a year, right? 2 centimeters or so a year. So I don't know what went wrong, but really interesting thing is that by being wrong, he was prophetic, because now we can, it turns out. And I'll show you how. We do it with geodesy, but now with geodesy, we need the space. It's another astronomical thing. So these are some of the first space geodesy measurements. They were based on a technique called very long baseline interferometry. We have a quasar, a very distant star that basically pulses, right? So sends out electromagnetic radiation, but it's not constant. It's high and low and high and low. It's like some form of noise in these things, right? So here are 2 radio telescopes. One is here on the American side, and this one is on the European side, and they will receive this noise, but they will receive it at a slightly different time, right? So in this cartoon, the North American station will receive, the radio telescope here will receive the noise a tiny bit earlier, and the same noise is being received by the telescope here. So you can correlate the signals received by the 2 radio telescopes. Keep in mind that the Earth is rotating in the meanwhile, of course, right? And what's called the phase difference, the difference in time of arrival of the signals, will be proportional to the distance between the telescopes. If the telescopes were in the same place, they would receive this thing at the same time. The farther away they are, the bigger the difference. Right? So it turns out, and our radio astronomy friends can do this very accurately. And I'm going to show you some data that were measured at these 2 radio telescopes. Not a cartoon now, they're real. There's a radio telescope here in Germany, Wetzel, Westford, I think it's in Maryland. And over 9 years, this is the changing distance between Westford and Wetzel. So the dots are the actual data measured at the different times. The arrow bars give you, you know, the kind of uncertainties in all the measurements. We span about 9 years. You can see at that baseline that the distance between the two stations has been increasing steadily. Right? All of these variability is due to things like atmospheric noise, you know, that affect this. And you can clearly see the trend is very well defined. And if you fit a line to this data, the lengthening of this baseline is about 18 millimeters a year. Right? Now we go to this map, and okay, so all right, so the baseline between these two, this is done with the Google Earth, right, where you draw the great circle between the points. This is here south of Iceland, right? South of Iceland, guess what? 1.8. So we can measure now the movement of plates, as Wegener wanted to do, right? It was this first thing. To him, I think, the impression was that this was the nail in the coffin, right? Measuring that these plates are coming, well, they weren't plates at the time, the continents had lifted, right? And we can do that now. And in fact, now it's not done with radio telescopes, but with GPS, you know, just the GPS that we all have in our phone. Of course, there are versions of these GPS receivers that are of very high accuracy. And then you put them in a stable station, like the one you see here. That's the GPS antenna here, a solar cell for power. Here's the data logging equipment. And so basically you log the position for a very long time, so you clear out all the noise that comes again from atmospheric effects and whatnot. And now we can really make a very good idea of how plates are moving and how plates are deforming. So going back to the time scale, what this is showing, the example I showed you for Eurasia and North America shows that large plates move at basically the same rate when they're measured over very different time intervals. When we use magnetic reversals, radioisotopic dating, astrochronology, etc., we really remember the first reversal, right, happened 700 plus 1,000 years ago. So you're really looking at things at the million-year time scale. Space geodesy, right, works at the 10-year time scale, right? That data set I showed you, right, span 9 years. And yeah, we can do a little better now with GPS, but you know, we don't really have long, you know, it's in the decades, right? Things are moving at the same rate. So that's not unexpected. In fact, in the geophysical, the geological literature, but this thing is not really trumpeted that much because it's exactly what we expect. You know, have a large plate, you can accelerate it or change its motion easily, right? And so yeah, they will move at that rate. It's pretty stable. It has to be. But I think the thing that unfortunately gets passed over is that this is a spectacular confirmation of this way of measuring geologic time. A spectacular confirmation of using the magnetic reversal record, the radioisotopic dating, astrochronology. It really works because we have this completely independent evidence on the data. In fact, what people are, you know, in this business are more interested in is when these two are not the same. That is telling you that between something like 700,000 years ago and the present, something happened that changed the plate. And that can happen if for small plates, places where there's, for example, there's mountain building, there's collision, or the formation of complex. But again, that's the spectacular confirmation. So I'm gonna finish here, you know, to remind again of this tiny, tiny bit that we inhabit. And I have a few quotes from this book that I highly recommend. So a meditation on geologic time. And these are quotes from Marshall Jones' book, that fathoming deep time is geology's single greatest contribution to human knowledge. And I think that's what we need. And we should keep in mind that the climatically stable Holocene, this is the most recent period, historical geological period, 10,000 years ago, so the end of the last glaciation, right, has been a very climatically stable in geologic terms, period. That's what allowed human civilization. That's when agriculture starts. That's when starts to develop. And time denial, the ignorance and even the denial of the existence of this deep time is she calls it a dangerous temporal illiteracy in our society. There's this wonderful image, like inexperienced but overconfident drivers, we just barge into landscapes and ecosystems with no sense of their long-established path. And then we react with surprise and indignation when faced with the penalty of ignoring this natural. So we have a distorted sense of humanity's place in the history of the natural world. And we really should see ourselves more as lucky inheritors and eventual bequeathers of the earth estate, as opposed to, you know, all of our thinking that we can do anything we want. Okay, no, we can't. We are in a speck in space and a speck in time. Okay, that's it.
Thank you very much. I have one other quotation about time that I'd like to share. Douglas Adams. Time is the illusion, lunchtime doubly so. As we're coming up to lunchtime, we have to double our efforts and go more quickly. Alberto, that was fabulous. We all, as teachers, have a general idea about geologic time, but background and how it was created and how we know these things, very helpful. And I'm getting thank yous from the chats now.
Yeah, so of course, you know, any questions, I'll be more than happy to answer.
Any questions from people on Zoom?
Yeah, can you hear me?
Yes.
Richard? Is there in the magnetic anomalies, is there a consistency in the distances between the anomalies, the reversing, or does it vary greatly?
So when we look at the anomalies, of course, we are measuring distances, right? So those distances will be different in different ocean basins depending on the spreading rate. If the spreading rate is fast, then the width of any one of those blocks will be greater.
Yes.
So for example, the Atlantic is relatively slow, the Atlantic Ocean. And so a given anomaly will be narrower in the Atlantic Ocean than say in the fast spreading Pacific. So there are some changes, and we have to keep keep track of all of that, yes, when we build the timescale.
But say mid-ocean ridge is there, it's moving at a constant rate, and so the distances will be the same.
Well, it turns out that the rates are not absolutely constant.
Okay.
So you have to take care of that. That's something that at the beginning, yeah, I didn't go into that kind of that level of detail, but for the first time scales, the idea was very simple, was to take essentially one or very few radiometric dates and then assume that spreading rate was constant throughout time. And then it was realized that no, spreading rates are not constant through time. They actually vary through time. And so They don't vary by tremendous amounts, but they do vary. And if you want to have an accurate counting of time, you have to take those variations into, you have to incorporate those variations. So that is done now currently when doing time scale.
How were the magnetic anomalies invented or first identified?
So they were identified because when ships went out, and it was really an exploration phase, they decided to measure the intensity of the magnetic field. But it wasn't, they weren't presuming that there were going to be these variations. It's a very cheap and very simple measurement. It's much simpler, for example, than measuring, say, gravity at sea. You need a gravimeter. You need to, it's complicated because the ship is moving, obviously, and it accelerates the instrument. But the magnetometer was very easy. You just put out the magnetometer and measure the magnetic field. And in fact, some of the first interpretations of these magnetic anomalies were that they were not due to magnetization of the ocean floor, but they were more like external phenomena. The magnetic field would vary during the day, for example, and so on and so forth. So, and then it was realized that no, I mean, they have this systematic character, and then we went from there.
I heard one story that they first were using the magnetometers to identify submarines.
Well, of course, for the military use of magnetometers is exactly that, to look for submarine. That is true. So sonar was very important in defining, if you will, the morphology, the shape of the mid-ocean ridge. So when I say, oh, the magnetic anomaly is symmetric about the axis of the mid-ocean ridge, well, the axis of the mid-ocean ridge is identified through sonar, right? Without sonar, we wouldn't know where the ridge is, what was the center of the ridge, basically. And so we wouldn't be able to place the magnetic anomalies in that context. Yeah, so those were absolutely critical, yes.
Would it spread faster at the equator?
No, that's not how it works. You can have fast spreading ridges away from the equator. The fact that it's true that now the Pacific rise is spreading very fast. It's not exactly at the equator, but it's sort of just of the equatorial belt. That's where they spread the fastest. But it doesn't have to be like that. You can have fast spreading ridges or slow spreading ridges that don't have to be at the equator.
The 30 degrees on either side.
Say again.
30 degrees above and below the equator. A lot of anomalies there for no reason.
So the pattern of the actual magnetic anomalies is complicated because I kind of simplify the picture a bit, but if you have to think of these bodies, right? They're magnetized. They're like prisms, right? And when they get magnetized, the direction of the magnetic field is not parallel to the surface of the Earth. It is at the equator. But as you go towards the pole, it starts dipping down. Now, what's also important is the orientation of these blocks, which could go, say, north-south, or they could go east-west, right? Depending on how they go, the anomalies get stronger or weaker. So a whole part of this Pacific rise, in fact, which is roughly north-south, near the equator, the anomalies are very low because it turns out that in that geometry, the anomaly just doesn't show up. And in other locations, the anomaly is very well preserved. So the example of the Altanin profile I showed you, or the southern South Pacific, there the ridge goes more almost east-west. So the magnetized blocks are almost east-west, and the anomalies come out larger. So there are lots of twists like that. Yes.
initially. And the strength seemed to go in a direction.
What picture was I showing when I was showing that? So let me see. You mean the cartoon?
Down,
Yeah, the
down, right there, up one.
west, that one. No, yes.
Oh, okay, so it's.
So that's just a
negative,
cartoon. It's
okay.
not a real,
Oh, no, I wasn't saying that, I thought that it was strength. No. Forget it.
okay,
Oh, one down, two down,
two down. That,
one more.
that.
Yeah, okay, thanks, man.
Yeah, well, now
sorry,
this
this
thing
is
goes
more
away.
right.
Okay, oh, yeah, I think I know what you mean. So let me pull this up. I think you want this one, right?
Yeah.
That's right. So this is, again, it's a cartoon, right? So
Oh,
they're
no, I
simplifying.
understand that, it was, I thought it was the strength of the signal as opposed to that it was a positive, okay.
No,
Sorry about
the idea here is that the arrows up and down are kind of giving you an idea of the polarity, right? But in fact, you have to think of a vector in three-dimensional space. So you have, this is where the interpretation needs work. You have to have, first of all, you have the shape of this prismatic body, right? Which has an orientation, right? And then there's another vector, which could be along the strike of this body or not, right? Which is the vector of the magnetic field. And there's the present magnetic field, and then there's a vector of the magnetization, which could go, right, in different directions. So it's a big vector sum, if you will, of it. Yeah.
I mean, clearly you can see the symmetry left side, right side.
Right. Well, we
My
should look at
question
the real
is,
thing. Yeah.
The duration it takes for the reversal. Some of the block are wider, wise, it took longer
Yes.
to reverse.
Yes. So let me show you something. Yes, absolutely. Let me show you a event slide. Just give me a second. You gotta find the event slide.
Sorry, may I just?
Yeah, go ahead. Yes,
So,
please.
just going on point, each of these reversals would then in fact be almost the same amount of time.
No, it's not, and that's the point of this. So
That's why
they're not the same amount.
Okay.
So let me. Okay, I have to give me a second. I'm skip slide. Okay, all right. Now we're gonna see. Okay, so this is a compilation, right? So the work that I showed you that was done here was for the interval between 33 and 83 million years, right? This is a more complete compilation, right? So this is, again, black is normal, white is reverse. The black is the same direction as the present here. So time is going from here, 160 or so million years ago, towards the present at the top, right? And what you see is the black and white is the pattern of the reversals, and the red is the magnetic anomalies that are generally measured at the Earth's surface, okay? At the sea surface, I should say. And this is the oldest ocean floor, right? Okay. Now, you can see that at this time, let's walk through geologic time. Reversals happen pretty often, then maybe a little less, then it varies. And then there was this is called the Cretaceous Quiet Zone, KQZ, or the Cretaceous Long Normal. There's a very long period of time that's 10, 20, 30, 37 or so million years in which the field was steady. Then it starts again And as you go from here towards the present, it seems the rate at which reversals take place is increasing towards the present, roughly, in general. Why is that happening? We don't know. Okay, we don't know. This is an open question. Yes.
When all the plates were together?
Yeah, so when all the plates were together was actually even earlier than that. Pangea started to fragment. So remember, the oldest North Atlantic is 160 plus million years. So the Pangea started to fragment here. And by the time it starts, there's already a sizable Atlantic Ocean. Okay. So what we think is happening, the origin of the magnetic field is still also not, but we know the Earth has a liquid outer core. The liquid outer core is metallic, and you have this conductor that's convecting, right? So you have all of this happening. And we think that these convection currents, once you have a conductor that's moving, you can generate a magnetic field. And so the magnetic field, now, why did this happen? That it didn't reverse for a very long time, and then the rate of reversals changes through time. That's the part that we don't really know. But in a way, it's an advantage. We're lucky that this happened for the following reason. Suppose that this was a really regular thing. So every 10 million years, let's say, you go one way or the other. Now I can give you a piece of recorded magnetic anomalies or of recorded magnetizations in sediments, which is something else that we can do. But then we wouldn't be able to tell one from the other, right? If they reverse every 10 million years, they're going to be the same whether I'm seeing it something. But this is like a fingerprint. So from the pattern, I can kind of go back to where that pattern is coming from, right? Because it's so random. Right? Yes.
The rate at which the field is spreading, and it's spreading itself.
Yes.
As a very.
Yes. So that's why when we build these time scales, we concentrate on parts of the ocean. So let me go back to the right. So, for example, here, the previous map shows you that there's data almost everywhere, right? But here I'm saying, oh, for that, I'm going to use these kinds of profiles here, these profiles there, these profiles here.
You were saying the high speed, allegedly.
That's right.
Relatively high speed.
These are places where the speed, the spreading rate is relatively fast. And so the fidelity of the tape recorder, if you will, is a little better. The best one we can have, right? And so, you select those locations based on that, right? So we already know where the faster spreading rates are. So to go back to your questions about the equator, right? So it's true, the Pacific spreads very fast here, but the Atlantic does not, for example. So there isn't an immediate, equator equals fast spread. So probably through geologic time, if you go back and say how fast plates were spread in a different time, you would probably not relate it to simply related to latitude.
Alberto, do we see any correlation between changes in orientation and animal evolution?
An evolution. No, so one idea is, and I think you were asking this earlier, how long does it take for a reversal to take place? And they're pretty fast as far as we can, geologically speaking. So they take, a few thousand years, I think, for the future. What seems to happen, and we have some really high resolution records for the last reversal, is that first the strength of the magnetic field weakens and weakens and weakens. And then when it comes back in the other direction. And there are other times in which the strength weakened then it comes back in, but it doesn't go all the way down, and it just stays in the same direction. So there are also variations in the, it's called the paleo intensity of the magnetic field. And all of that changes, of course, right? And so,
Are weak trend then can last for a lot more time? Because we're in a weak trend now.
we are in a at the moment, the magnetic field seems to be weakening, but it's very hard to predict whether that will eventually lead to a reversal or whether it's just a temporary change. Now, the intensity is important because our magnetic field is part of the reason that we are shielded from solar radiation, right? From solar wind. And so when if the magnetic field were to completely disappear for a long period of time, there will be consequences definitely, because, you know, on life. But as far as we know, there isn't a clear link between reversals and extinctions, for example. People have looked for that because of this, because they thought when the magnetic field is really weak, maybe there's more solar radiation, which damages molecular tissue that could lead to extinctions. And so far, I don't think those preliminary. Yeah, you had a question.
Connection between like solar flares and like sunspots and stuff going on in the sun in relation to our magnetic field.
Yes, those are disturbances of the magnetic field. They will disturb the magnetic field, definitely. So all I was talking about was sort of the magnetic field, sort of the internal magnetic field generated by the Earth. But there's also disturbances of that, right? There are magnetic storms, for example. Right? So if you were to take a profile of magnetic anomalies during a magnetic storm, probably not going to be a good one. You probably have to toss it out, okay? But you know, generally those are episodes, right? And we know when they happen, probably after the fact more than predicting them. But you know, we can eliminate them. So, for example, the database that you see here, I mean, the you know, data are already cleaned out of those effects. But yeah, they exist too. Yes, there are changes, and there are changes all the time in the magnetic field. So, if you, I don't know how many of you are sailors or do any kind of, but if you look at a nautical chart, it will tell you about the declination, right? The angle between geographic north and magnetic north, right? But it will also tell you how fast that angle is changing. So the position of the magnetic pole is not exactly at the geographic pole right now. It's sort of in Hudson Bay. So here, if you go out, the magnetic north, right, is about 12 degrees, I think, west of geographic. But that is changing, right? And this is changing not very fast, but it's changing, you know, on human time scales, right? So on long time scales, the average magnetic field of the Earth is very close to a dipole along the rotation axis. So the north magnetic pole kind of moves around, the south magnetic pole does, but on average, right, they're aligned. And we think that has to do with the effect of the Earth's rotation on the convection in the outer core.
Would now they would they disregard that now using GPS? That's more accurate.
Yes, you could use GPS. That's true.
Rather than using the
you know, there's a big advantage to knowing these sort of more primitive, if you will, techniques. If your battery goes out or something happens,
right,
you want to have a good backup. So if any of you is interested, there are some fantastic publications on the navigation art of the Polynesian people. And they didn't have any compass, they didn't have any nautical chart, but they had an established technique, a craft to navigate between very distant islands. They could go from an island to another that was way over the horizon. And they used the stars They were very sophisticated. They used the point at which stars set and rise. And that's a fixed point of the compass. That doesn't change, stays the same. Of course, there are different stars that rise and set different times in different seasons, but that point stays the same. So they use those points, they use the direction of the swell, and then when they got close to the islands, they used clouds, they used birds. They had a very developed art of that, and they had no metal, no compasses, no nothing, right? And so you could kind of start with that very low tech, if you will. Then the step up is to have a compass and a nautical chart, and the next step up, of course, is GPS. So now people use GPS all the time, but you know, if you go to sea, it would be very useful for you to have the skills to be able to navigate through a compass.
I've just spent, I guess, 2 weeks in Hawaii.
Yeah.
That colony.
Yes, it's an amazing art. It's astounding. Yeah. What they could do is
Myself, if I go to that.
not zero. No compass. Think of no compass.
Let me just throw one thing in quickly about that. At the Margaret Mead Hall of Polynesian People, or Pacific People, at the Museum of Natural History, they have some sections where they describe this, and they have some the kinds of maps that they made.
Yes. Yes, yeah.
So you may want to dig that out next time you go to the museum.
I just had a question about GPS. I know that or I heard that the government scrambles it somewhat to make it less, not so accurate that it can be used. So you have access to the real GPS as opposed to what we have on ours.
So I thought, so I'm not a GPS expert, okay, but I thought that these scrambling was kind of taken away.
Okay.
Yeah. But at any rate, even with the super perfect one, if you're really looking for things like, you know, movement of this much a year, you really need to sit the antenna there fixed for a very long time, because they're just noise, basically, right? And you know, even with the GPS working at its maximum capacity, you will still get noise from, again, atmospheric phenomena, magnetic, not necessarily stored, but just even small fluctuations and so on and so forth. So the secret is in averaging, basically.
So that the algorithm corrects for this, essentially.
Well, if it's most of it is simply what we call stacking or average. If there's noise, right, it's gonna pull you one way at some time and pull you the other way at some other time and pull you this other way, blah, blah, blah. But if it's not systematic, right, if it's not always pulling you the same way, right, but it's simply randomly going about, you just take the average of everything and you will get a much better idea of your position. And the longer is your observation period, the better you can average. So I think that's the answer for that.
Okay, I think we'll call it. No.
Okay.
We'll see if we can come up with the Polynesian map.
Yeah, so I can suggest a book. Let me see.
Again, Alberto, thank you very much for sharing your
I'll
knowledge.
send
Thank
you
you.
something, you know, and then.
Okay, I'll put it onto the website.
I'd rather not.
I'll be sending everybody a link to the certificate a little bit later. I know at least 2 of us are a bit jet lagged, bragging. So I think we'll call it an end now. Thank you very much. We'll let you know when the recording is available.